Okay, so this is chapter 6. We will look at applications of Newton's laws. And again, Newton's laws are, so the second law is force equal to mass times acceleration. The first law is a special case of the second law. The first law says if the force is zero, that tells you, of course, acceleration is zero, which tells you, what does acceleration equal to zero tell you? Yeah, so if you're at rest, well, you'll be at rest, so your velocity will be constant. Okay, so the first law is a special case of the second law, and it was actually discovered by Mr. Galileo, but since it's a special case, we call it Newton's first law. And what is the third law? Yep, so forces always come in pairs, and if this guy is acting on him with a force of F, this guy reacts with a force equal and opposite force. Okay? All right, so this chapter, as it says, it's the application of these laws. Okay? Essentially, it's an application of this law, Newton's second law. We'll look at objects, we'll see what their acceleration is, what the acceleration of the object is, and figure out where the force is coming from. Figure out what force is giving the object that acceleration. Okay. Or if it's not accelerating, then we'll look at all the forces acting on the object and make sure that they all add up to zero. They will add up to zero. Okay. So it's just looking at where the forces are coming from. All right, so here's Newton's first law, which is a special case of the second law. The net force on this is zero. Here's gravity, and the air is pushing up on it, again, with an equal and opposite force. And the net force on this is zero. And if you push it in this direction, if you set it in motion in this direction, the friction force is negligible. Okay, and that was the whole purpose of this bed of air, okay, on which it's floating. Okay, and so if you push it, it'll maintain a constant velocity, and that's so different from your everyday experience that it's exciting. Yeah. So Newton's second law says, here's an object, there are several forces acting on it. Force of gravity, there's the normal force, here's friction force, and if you're pulling on it with this force, okay, this vertical force adds to that normal component. So the vertical component plus the normal force plus this force add up to zero, because this guy is not moving in the y direction. And this x component of this tension has to be greater than the friction force for this guy to accelerate in this direction. If the x component is equal to that, he'll move with a constant velocity. Okay? So we'll apply this equation to the situations like this. Of course, this is a vector equation, and in 3 dimensions, it's 3 equations. You saw that the x component of the force can only... I got it. I'll be back. Hello? All right, you saw that the x component of the force can only affect motion in the x direction. So the x component can give you x acceleration, y component gives you y acceleration, and so on. Newton's third law tells us that all forces come in pairs. If she's applying a force on the wall in that direction, the wall exerts an equal and opposite force on her. Okay, so the action and reaction are acting on different objects. Yeah. So for instance, here's an interesting application. Let's say the earth is pulling you down, and if your weight is, let's say, 150 pounds, okay, you're pulling earth with the same force, equal and opposite force. Okay, we'll use a lot of this free body diagrams. Okay. What we'll do is we'll look at a situation that we're analyzing, and then we draw only the essential parts. Okay. For now, we'll look at when forces are acting on an object, the object won't spin. If it moves, it'll only move, it will only have translational motion. So we'll be able to treat this object as a point object. Yeah. Now, so let me show you a couple of examples. Okay, so here's the center of mass of the object. If you apply forces that all go through the center of mass, then this object won't spin, no matter how many forces you apply. If all the forces go, the line of action of all the forces is through the center of mass, it won't spin. The best it can do is have a translational motion. All right, now I can show you other situations where will this object spin? This won't spin either if this force is equal to that and the line are equidistant from the center of mass. Okay, so this won't spin either. Now this guy will spin. Okay, so we'll consider situations when the object is not spinning. Okay, and in all those situations, what we can do is we can treat the object as a point object, and all the forces will be acting through that. Okay, all right. So we'll consider spinning objects in chapter 10. All right, so here's this object. You're interested in, you see this kind of stuff all the time, this kind of, how many forces are acting on this guy? 3. This tension, that tension, and the weight. Okay, now since this guy is not spinning, okay, all the forces are such that, well, so you can treat him as a point object. There's that object, there's the tension, there's the other tension, and there's the weight of the object. Okay, so here's the real physical situation, and this is what we'll analyze. Okay, and what does Mr. Newton tell us? This guy is at rest, his acceleration is 0, so the net force on him must be 0. So the sum of those 3 vectors must be 0. Yeah. Here's a barge. He has linear acceleration. It's not spinning. Okay. So there's this force that's being applied by this tugboat. This force is passing through the center of mass. This force is also applied such that it's passing through the center of mass. Now, if another boat pushed in this direction, then the barge would spin. Okay. So here we are applying forces through the center of mass. There's a third force on it, the drag force. What is the drag force?
The water.
The friction force of the water, which is effectively acting at the center of mass. Okay. So those are the three forces acting on the object. There's the object. Okay. And since the object has an acceleration, the sum of these three forces, there's the net force. That is giving the barge an acceleration in that direction. Okay. Anyway, what you want to learn is the skill you want to develop is you look at an object, you don't want to be drawing this. This is for kids. You guys are all in college. This is the drawing you do. Okay? Okay, so this is called a free body diagram. All right, here is this guy riding an elevator. In this diagram shows all the forces acting on the object. But if you were interested in just the motion of this guy, you don't want to know all those forces. You don't care about all those forces. All you care about is what are the forces on this guy. Okay. But let me go over all the forces here. This is the tension in the cable that's pulling up the elevator. This is the weight of the elevator itself. Okay. This is the weight of this guy. Gravity is pulling him down. And the only other force, he's standing on the scale that's pushing him up. Okay. And the force of this force gets translated to the floor of the elevator. Okay. And this is the weight of the scale, which also gets translated to the elevator. Okay, those are all the forces acting on him. But if you're interested in just this guy, there are only two forces acting on this guy: the force of gravity and the force that the scale exerts on him. So there's the guy represented as a point. There's gravity pulling him down, and there's the force of the scale. So if you look at this diagram, can you tell me what's happening? He's accelerating upwards. Mm-hmm. All right. So here's a composite object. Okay. What does Newton's laws apply to? Every object. Okay, so if you have a composite system, Newton's laws applies to each object. Okay. Now, for now, what we'll consider is we'll consider systems, pulley systems, where they're massless and frictionless. Okay, if the pulley system is massless and frictionless, then the tension in the string is the same. Now, in a later statics class, you'll study systems where pulleys, the mass is not negligible, and then the tension on the same rope will be different. Okay, but for now, we'll keep it simple. Okay. So here's a composite system, and we'll apply Newton's laws to each object separately. Okay, of the system. So on this guy, there's this force of tension, there's this weight, and there's the normal force. And if there was friction, the friction would be acting like that. Okay, so the forces on this guy are the tension in this direction, his weight, and the normal force. And you can see that there's no friction. Yep.
Why is it that for mass one,
Mhm.
the weight force is pointing down into it, the normal force is pushing up, but for mass two, the weight is like,
Oh, that's
is
just,
that just irrelevant, or is that,
yeah, that's not relevant.
okay,
That's just, I guess, a space issue.
okay,
Yeah. Yeah. And also, they didn't draw this as a point because they wanted to show that this was mass M1 and M2. But since you're more sophisticated, you would have done this. Right. All right, so the point is, you apply Newton's laws to individual objects in that system, in the composite system. Okay. Here's something called Atwood's machine. Mr. Atwood this sort of invented this to measure acceleration due to gravity. Okay. Back in the day, when see, you can relate the acceleration due to gravity. Okay, what you can do is you can drop this object, time it, measure how much time it takes to fall this distance, and then you can calculate the acceleration due to gravity. What was the problem 200 years ago?
Wasn't very accurate.
I'm sorry?
They weren't very accurate.
What was not very good?
I guess it would be time, distance.
So, no, distance is, so measuring the time was the problem. So if you could somehow slow it down, then you could measure the time more accurately. If you had to measure 10 seconds, you would make a smaller error. But if you had to measure 0.3 seconds, you'd make a larger. Okay. So this device essentially allowed you to slow things down. Okay, so if this guy is heavier than him, you'll have a net acceleration in this direction. Okay. And if the masses were equal, the acceleration would be 0. And if this mass was 0, this guy would have an acceleration of g. So here was a machine where you could tune this acceleration to be anywhere from 0 to g, depending on the masses. Okay, so that's what Mr. Atwood did. And we'll see later, again, you're using massless pulleys, so the tension here is the same as the tension there. And the acceleration works out to be m2 minus m1 divided by m2 plus m1 times g. Okay. That's assuming m2 is greater than 0. M2 is greater than m1. Okay, so here is a machine where you can tune the acceleration to be any value between these two. Anywhere there. All right. Now we'll talk about friction forces. So friction forces are important. Sometimes they can be a nuisance, but okay. What do friction forces do? So let's say here's this object. I gave it a push, and it slowed down. Why did it slow down? Friction. Okay, so it was moving in that direction. Friction was acting in a direction opposite to the motion. Okay, if it's moving like this, the friction force is acting like that. If it's moving like this, friction force is acting like this. Okay. What happened to the kinetic energy of the object? It got turned into heat. Okay, so friction forces are called dissipative forces. It's a dissipative force. It dissipates mechanical energy. Okay. Mechanical energy is kinetic energy and potential energy. Can energy be destroyed? No. What happened? It got converted to heat. Why would you call it a dissipative force? I mean, you didn't destroy the energy. All you did was converted it into another form of energy.
It's just as you're converting it, you're no longer moving.
No, you just converted. I gave you 4 quarters instead of the dollar.
You're dissipating the desired force?
I'm sorry?
You're dissipating the desired force?
So mechanical energy is kinetic energy is a good form of energy. Heat is the worst form of energy. Okay, so if you have kinetic energy, you can convert it 100% to potential energy, which can be converted back to 100% kinetic energy. Yeah. Heat on the other form, that's what you do in your car. You burn gasoline, you generate heat, and you try to convert that into motion of your car. Only about 20% of that is converted to motion. Yeah. So heat is the worst form of energy. All right, so friction forces are dissipative forces. Okay, so for instance, if this if this guy is trying to move in this direction, if you look at the two surfaces, there's points in contact. Okay, and there are loose bonds being formed. So if the object is trying to move in this direction, these bonds are pulling the object back in that direction. If the object is trying to move in this direction, the bonds are pulling in that direction, and to move, you have to break those bonds, and so that's you're spending energy there. Okay, and that's how it's converted to heat. So part of the friction force is because of the roughness of the surface. Okay, you gotta overcome those barriers. However, much of the friction force is due to the attractive forces between the molecules of the two objects. Okay. In fact, perfectly smooth surfaces of similar material would adhere, forming a cold weld. So if you had a single crystal, it's just atoms arranged and you can't slip it off. Okay. So two surfaces in contact, the actual contact area is only about 1 part in 10,000. Okay. So for instance, for this tablet sitting on the table, only the total area of contact is roughly just the size of this pencil tip. Okay. Now notice something. So there's friction between this object and the table. If I push down on this object, what happens to the friction force? It increases. Why did it increase? You're forcing there more points touching. Okay. All right, so the friction force depends on the normal force. Okay. Normal forces on the surface. All right, so we're talking about friction forces. That's the term used when two solid surfaces are in contact. And there's two kinds of friction forces, static friction forces, and kinetic friction forces. Static friction forces are the forces between two surfaces that are not moving relative to each other. Okay. And kinetic friction forces are the friction forces between two surfaces that are moving relative to each other. Okay, so why do we have these? So let's see. All right. Okay, so you can see that this guy is pushing with a force of 10 newtons and the object is not moving. So that's because there's a friction force between the two of 10 newtons in the opposite direction. Okay, now you're pushing with a force of 25 newtons and there's a friction force in the opposite direction of 25 newtons. And this is called a static friction force. So you can see that the static friction force can vary. Okay, so if those molecules holding onto the upper molecules, if you pull them harder, they can pull back harder. Okay. So the static friction force can be anywhere, and again, if you were pushing, oops, if you were pushing in this direction, the static friction force would be in the opposite direction. Okay. So all two surfaces, there will be a maximum static friction force for two given surfaces. Okay. So you can see that the maximum static friction force well, it's still not moving. So we haven't reached the maximum static friction force. Oh, there you go. Okay, so okay, so here you applied a 75 Newton force and it's moving. So the maximum friction force was around 125 Newtons you saw. And now I'm applying a force of 110 Newtons and it's moving. So you see, once the object moves, the friction force, the kinetic friction force, is smaller than the maximum static friction force. So it's hard to get an object to move, but once you get it moving, then it's not as hard to keep it moving. Okay, so the kinetic friction force is always smaller than the maximum static friction force. All right, so you apply a force and the static friction force is preventing you from moving. So what we do is we make this force larger and larger. So that's what this graph is. Here's the applied force and this is the friction force. So when the force is smaller than that, in our case smaller than 125 Newton force, the static friction force was equal to that and the object didn't move. Once you applied a force greater than that, the object started moving, and then the friction force was kinetic friction force, and that is constant. Okay, so if you apply greater force, if you apply this force, the kinetic friction force is that much, which is smaller than that, and the object accelerates. Okay, so once you apply a force greater than that, the kinetic friction force is constant, and this guy is greater than that, and he will keep accelerating. Yep.
On that graph, is the y-axis the amount of force being applied to the object?
No, x-axis is the force being applied. Yeah. On the y-axis, it's either the static friction or the kinetic friction.
Oh,
Okay, so once you apply a force, so the friction force is has a maximum value. So the static friction force, so friction forces are denoted by little f. The subscript tells you whether it's a static or a kinetic friction force. S for static friction force, K for kinetic friction force. The static friction force is less than a maximum value. This guy is called the coefficient of friction. That's a measure of, can you tell me what is the dimension of this? So this is a force, that's a force, that's the normal force. So this guy is a dimensionless quantity. Okay. What it tells you is how sticky the two surfaces are. Greater this value, greater the friction force. Okay. So this tells you the stickiness of the two surfaces. All right, there's the maximum static friction force. This is the normal force, that normal force. Okay. So for instance, if you push down on it right now, the normal force is equal to the weight of the object. But if you push down on it, the normal force is greater than the weight of the object. and the friction force increases. Yeah. So the friction force depends on the normal forces. The kinetic friction force is given by a similar formula. This is the maximum static friction force. Here's the kinetic friction force. It's mu k times the normal force. So since this guy is bigger than him, this guy is bigger than him. The static coefficient of friction is always greater than the kinetic coefficient of friction. All right. So here are the coefficients of friction. These numbers are important enough that anytime there's a table of numbers, they're important enough in your life that somebody's gone to the trouble of measuring them. Okay. Rubber on dry concrete, rubber on wet concrete. Why would somebody measure this? I'm sorry? Yeah, so you're using this all the time. Okay. You guys have heard of anti-locking braking system? Yeah. All right. So let me give meaning to these numbers first, and then we'll talk about the anti-locking braking system. Okay. So this is mu k is 0.8 and mu s is 1. Okay. So what we'll do is, we'll look at a sort of an example. Let's say a 100-pound rubber block sitting on concrete. So the normal force is 100 pound. The maximum static friction force is mu s times the normal force. And the static friction force is 1. So 1 times 100 pound. So to get this block moving, what you need to do is you need to apply a 100-pound force for a rubber block sitting on concrete. But once you get it moving, all you need is 80 pounds to keep it moving. If you apply an 80-pound force, then it'll keep moving at constant speed. Okay, so that's what these numbers tell you. So if you have a 100-pound rubber block sitting on wet concrete, all you need is 70 pounds to get it moving. Yep.
Is the highest number given 1, or is that just like part of the example?
Okay, so you tell me, can the highest number be only 1? Let's put glue on this thing. What happens to that number?
It's higher.
There you go. So that number is dimensionless, but it can be anywhere from 0 to infinity. Yep. All right. All right, so here's the idea. You've seen this guy. X minus x naught. So let's say this was your initial speed of the car and you want to stop the car. So if you're moving in this direction, of course, the acceleration has to be in that direction. Okay, greater your deceleration, greater the acceleration, smaller the distance over which you stop. Okay, so that's what you want. You want to stop as fast as possible, of course. Okay? Now, if you're driving, okay, and let's say in a panic situation, you pump the brake, you lock the wheels, and now the wheels are, so you were going in this direction, you're sliding, the acceleration is in that direction, but if your wheels are sliding, that you're employing kinetic friction forces. The kinetic friction force is mu k times mg, your weight. So your acceleration is mu k times g. Okay, and you saw that mu k times g, that's 80% of g. So if your wheel's locked, then the maximum acceleration you can have is 8 meters per second squared. If you didn't lock your brakes and if you were employing static friction force, then you could have 1 times g, 10 meters per second squared. Okay. Well, what does that mean? Okay. So what you do is when the wheel is rotating, see this point, so when you're trying to slow down, the wheel will want to rotate that way, and if you have this point is in contact and the contact point is preventing it from sliding, the static friction force will be in that direction. Okay. So what the anti-locking braking system does is it's pumping the brake for you, so about 15 to 20 times a second. It's locking the brake, unlocking, locking the brake, and unlocking. So the wheels keep rolling, okay? And since it's slowing down, the static friction force is acting in this direction. And the maximum static friction force, so the acceleration is mu s times g. You have a larger acceleration, your stopping distance is smaller. Yeah. Nowadays, all cars have anti-locking braking systems. But I'm old enough where I've driven cars which didn't have anti-locking brakes. And then your insurance was higher. But now your insurance is higher because you're texting and driving. All right. So here's a fella skiing down. Okay, there's the free body diagram. There's the weight of the guy. But what is more useful is the component of the weight along the slope and the component of the weight perpendicular to the slope. The normal force balances that, and there's a kinetic friction force. So those are the forces acting on this guy. And if this is greater than that, then he'll accelerate downhill and so on. Okay. The friction force is related to this normal force. Okay. So for instance, if he was skiing down a vertical wall, again, the normal force would be 0 and the friction force would be 0. But that he would be free falling. Okay. Yeah. So here's an important diagram. Okay. So when this guy accelerates, when the truck accelerates, the truck engine provides the thrust for this guy to make him accelerate. What is making the box accelerate? The static friction force between the bed and that. Okay. So for instance, if this was a ice bed and a heavy block, you accelerate and you leave your load behind. Okay. Now, of course, these semis can't accelerate fast enough where you would have to worry about that. What you have to worry about is the following. Let's say you're driving the semi and a wall jumps in front of you. Okay. If a wall jumps in front of you and it stops you, you're hoping that the static friction force will stop this guy. If the static friction force is not large enough, then this will keep coming at you. So you get a double whammy. Yeah. The wall in front and the heavy load. And this happens all the time. So what do you do if you have a super heavy load?
You strap it down to add more forces, that'll keep it down.
Yep, you chain it down. Yep. To prevent this from happening. All right, so you're going in a circular road. The engine provides you thrust in the forward direction. But to go in a circle, what you need is a centripetal force. So you need a force in this direction. What is giving you that force? I'm sorry? Well, you're not moving in this direction. It's the static friction force that's provided. Okay. How do you get friction forces? How does the friction force arise?
The things touching each other, like the bars.
Yeah.
You have a very rough road and then the tires that like attract.
So the bond between the tires and the road, attractive forces between the bond and the road. Well, if you keep circling around, what will happen? Okay, you are leaving some rubber, the road attracting the rubber molecules. Some of the rubber molecules get pulled onto the road. So if you did that, if you kept going in a circle, you're leaving rubber on the road. Okay? Now, why are we talking about this? It turns out that if every road, every turn was flat, if the road were flat, then it would cost us billions of dollars a year in rubber. That's how much rubber you'd leave on the road. Literally. Okay, so as an engineer, what do? You go home and think about it and see if you can solve this problem. What's that? There you go. All right, so if you make a pitch on the road, now the normal force is like that. There's the weight. This component of the normal force is balancing the weight. And this component of the normal force is providing the centripetal force. Okay. So, if the pitch is that, and if you go at this speed, then that normal force will provide the centripetal force. If you go faster than this, then you'll need a static friction force. If you go slower than this, then you'll need a static friction force in that direction. There's something very interesting about this formula. Can you tell me what's interesting about that? See, the mass of the vehicle is not in there. It could be a semi or a car or anything. So you see that speed limit, that the speed that's marked on exits, that speed is such that you don't need any friction forces. So even on the iciest conditions, if you go at exactly that speed that's marked on the exit, you won't come off the exit. Whether you're driving a truck or a car. All right, so this not only saves the nation billions of dollars, but it's also a safety thing. Okay? So we live in a race town. Have you guys ever walked on that on the speedway? It's pretty cool because that turn is banked at 30 degrees. And so if you drive less than at 90 miles an hour, you will not be using any friction. 90 miles an hour. Okay? If you drive less than 90 miles an hour, the friction has to be in this direction, preventing you from slipping down. And of course, if you drive faster than 90 miles an hour, the friction has to be in this direction, okay, to prevent you from sliding away. Okay. Of course, when you're flying, you're not in contact with the surface, so you have to bank your plane to provide the centripetal force. So the lift is in this direction. This component of the lift is balanced, preventing you from falling off the sky. And this component of the lift is providing you the centripetal force. Okay. Okay, so friction forces are when two solid surfaces are in contact with each other. Okay, so if this guy is moving like that, you have a friction force in this direction. But if you're falling through a fluid, so let's say you drop a cat, here's the force of gravity, the air exerts a friction force on the cat. And if you're falling through a fluid, that friction force is called a drag force, just a specialized name. Okay. Now, if it's a large object falling through air, then it turns out that this drag force is proportional to the speed square. So the drag force depends on the speed. See, this friction force does not depend on the speed. When you're falling through a fluid, your friction forces will depend on the speed. So for large forces, it depends on speed square. If it's a tiny object, then it only is proportional to the speed. So we'll consider two different classes of drag forces. Okay, so drag forces that are proportional to the speed square and drag forces that are proportional to the speed. This is for large objects, this is for tiny objects. All right, so let's do this experiment. Let's drop a cat. So when you first drop a cat, what is its speed?
Speed of gravity.
0. So the drag force is 0. As it acquires speed, as it speeds up, the drag force starts increasing. As this force starts increasing, well, eventually as long as this force is smaller than this force, the cat will keep accelerating and speed up. Eventually, this will equal that force, the force of gravity, and now it's not accelerating anymore. So the cat has reached terminal velocity. Okay. And this in the animal world, squirrels can jump off large trees and not hurt themselves. Okay. So they reach in a small enough terminal velocity which doesn't cause them damage. Okay, so the drag force is proportional to the speed square for large objects. Okay. This is the density. This is the density of the fluid in which you're moving. This is the area of cross section. Let's say if you're falling this way, that area, that's that area, and this is the drag coefficient. Okay. So when you're driving your car, do you guys know where you're spending all your gas, your most gas? Pushing air out of the way. Half your gas is for that. Okay. So you try to minimize this drag force by making the car aerodynamic. What you're trying to do is reducing this coefficient. Okay, so for your car, this number C is better than for the UPS truck. Okay. All right, so there's the drag force. Okay, so when you have reached terminal velocity, the drag force is equal to the weight. Okay, and so here's the formula for the terminal velocity. So the terminal velocity is 2 times mg, the drag coefficient times the density of the fluid in which you're falling times the area of cross section. Okay, so you see the terminal velocity for this guy is smaller than the terminal velocity for this guy. Why is that? It's the same guy. Yeah, the area is larger than, okay, this area is larger in that configuration. Yeah. So here's terminal velocities for various objects. So for raindrops, the terminal velocity is about 9 meters per second, about 20 miles an hour. Okay, this doesn't hurt, so you can walk in the rain. Hailstones, this is about 35 miles an hour. You don't want to walk in hail when it's hailing. You definitely don't want to walk when it's raining golf balls. So here's the terminal velocity for a baseball. See, that's faster than 100 miles an hour. So I can throw a baseball faster than 100 miles an hour. All I have to do is go high enough up and drop it. Yeah. Okay. So for small objects falling through a fluid, the drag force is proportional to the velocity. Okay, so for when object is very small, is going very slow, and it's traveling slow, or it's going through a denser medium than air, the drag force is proportional to the velocity. Okay. And in this formula, eta is the viscosity of the fluid. Okay, so for instance, if you, let's say you shoot a marble through water or through honey, the drag force through honey would be larger. This is larger. Okay, the viscosity is larger, and r is the radius of the object. All right, so for small objects, the drag force is proportional to the velocity. So Coriolis force, you guys have heard that in the northern hemisphere, when you have a low pressure, you get a counterclockwise circulation, and around a high pressure, you get a clockwise circulation. Yeah.
This is more going back to the drag force and Stokes' law, but
Mhm.
at what point does something get small enough that you can use Stokes' law? Like, where's the boundary there?
I don't know the clean answer to that. Chat GPT. All right. So we'll see how this happens. Okay. You guys know what is the radius of the Earth?
6,000 something kilometers?
Yes, 6,400 kilometers, about 4,000 miles. And so the circumference of the Earth is 2 pi r. That is 6 times 4, 24,000 miles. And it takes 24 hours. So if you're standing at the equator, you're going at 1,000 miles an hour. So let's say we are at the equator. The ground is going at 1,000 miles an hour. What's the speed of this air? If you're Santa Claus, how fast is the ground moving?
Close to 0.
0. So the air is also 0. All right. How about if you're in New York? So this air is moving at 1,000 miles per hour, and this air is moving at 700 miles per hour. Okay. So now what we'll do is we'll create a low pressure area here. Okay. What happens? Air moves from high pressure to low pressure. So some of this air starts moving like that. Well, it had a 700 mile an hour velocity component here, but the ground here is moving at 800 miles an hour. So this air falls behind. This air that was moving up, this was moving at 1,000 miles an hour. This guy is only moving at 800 miles an hour. So this air will go forward. Okay. Well, the reason it's called a Coriolis force is, if something doesn't move in a straight line, you say that there must be some force acting on it. Okay? And we call it a Coriolis force. It's not really a force, it's relative motion. You are looking at it from a non-inertial frame of reference. Remember we said that a non-inertial frame of reference is a frame that is accelerating. So if you're standing on the ground is accelerating because you're going in a circle. Okay? So when you're looking at it from a non-inertial frame of reference, you have to come up with a non-existence force, existing force. Okay, so similarly, you can argue if you're at in a high pressure, this in the northern hemisphere, you'll have a clockwise rotation, and it's the opposite in the southern hemisphere. Okay. Who taught the geese to formation fly? What's that? I'm sorry?
Evolution.
Okay, why did evolution teach?
Because geese have spent more energy than they get to reproduce.
I'm sorry?
The geese have spent more energy than managed to migrate to reproduce.
Well, so if a geese has to go from point A to B, would it spend the same energy flying alone or no? So it formation flies because you spend less energy in going from point A to B. You guys have seen cyclists drafting, and so you can do you cycle? No. What's that? Okay. You can spend if you draft right, you can spend 50% less energy. So those guys in Tour de France, the team members, that's what they're doing. They're doing work and providing you the draft, so they get paid. So this guy is working the hardest. These guys drafting are working less. And apparently this configuration is also good for communication. All right, so here's the next question for you guys. This guy's working the hardest. What's in it for him?
You'll eventually get to swap out with someone else.
So every 5 minutes they swap out. With that strategy, let's say if one geese went from point A to B and spent 1,000 joules, by adopting this strategy, maybe each geese will only spend 800 joules. Okay? I'm just making up the numbers, they're not accurate. Even ChatGPT won't be able to answer that, but anyway, that's the idea. And that's why evolution chose it. Yep.
Why does flying in this formation make the same energy?
So we said, have you drafted a semi on a highway?
I don't know what that means.
Well, don't be doing that. At least I didn't tell you to do it. So here's the semi going, and you drive close behind the semi, your gas mileage will go up.
Oh, sure.
Okay. So this guy is making all the air go there. There's partial vacuum, and you're
Okay.
okay. Yeah. So yeah, that's why your gas mileage will go up. Yep.
And in the same context, when you pass a semi,
Mhm.
the car set pushes away from it because the front of the semi is pushing the air away from the front.
Say that again.
Similar to the context of the vacuum behind the semi,
Mm-hmm.
when you drive past a semi,
Mhm.
there's a little bit of your car you can feel being pushed away from the semi because of the air being pushed away from the front of it.
Okay, you get pulled towards the semi. Okay, so here's what. So we're going to look at it from the top. And when you come to chapter 14, we'll learn about this. So these guys are going like that. The air is being pushed away. This air is going fast. And when air is going fast, the pressure is lower. So the pressure is high here, and you get pushed towards the semi.
then when you get closer to the front,
Yeah,
you
then,
get pushed away.
okay, I don't know. So yeah. Okay. All right, guys, so that finishes this chapter.